Hello everyone, welcome to our YouTube channel Metallurgical Engineering. So in this video we are going to discuss about few more important interview these questions for metallurgical engineering. So the first question is, what is the difference between ferrite, austenite and martensite in steel? So they are the important phases which formed in steel. So the first one is ferrite, which is the ferrite is soft ductile phase of iron with BCC structure. So the main difference between these three is the crystal structure. Ferrite is BCC, austenite is FCC, and martensite is BCT. This is the important, most important difference between these three different phases in steel. The other factors is like this ferrite is soft as well as it is more ductile, and the another thing, this ferrite could be formed at this low temperature, which we called as alpha ferrite, and at higher temperature phase is called as a delta ferrite. And this is and the main property of the ferrite is it is magnetic and relatively soft and ductile. And let's come to the austenite. So austenite is having a FCC crystal structure, and another thing about austenite is that it form above 912 degrees Celsius, and that is for pure iron. And the another thing is that it is highly ductile phase, and also it is non-magnetic. So the main difference between austenite and ferrite is that ferrite is magnetic and austenite is non-magnetic. And then let's come to the martensite, which will form when austenite is rapidly cooled, resulting in the very hard and brittle structure, and the crystal structure is body centered tetragonal. So this is the main difference between ferrite, austenite and martensite. So the another question is, explain the difference between TTT diagram and CCT diagram. So this TTT diagram is like time temperature transformation diagram, and the CCT diagram is continuous cooling transformation. So the main difference between these two is that the time temperature diagrams basically show the transformation of austenite under isothermal condition. So here we are talking about isothermal condition, while in this case of CCT diagram, it represents transformation that occur during continuous cooling, which is more practical for industrial processes. So these are the two main difference, but there are some other difference as well, which we have discussed in the other videos. If you want, you can go there and watch it. And now let's come to the another set of the problem. So the next question is, what are the effects of chromium, nickel and molybdenum and carbon on stainless steel? So this is very important question. So basically chromium will provide a corrosion resistance, which is more obvious, as you know that in stainless steel you require minimum 10.5% of chromium. So the definition of stainless steel is that you have this minimum amount of chromium in the steel, then it is called as stainless steel. And nickel stabilizes the austenitic phase. Molybdenum increases the corrosion resistance, particularly against pitting and crevice corrosion. Carbon affects the hardness and strength, but can also lead to carbide precipitation, which might reduce corrosion resistance. So that's where this chromium is for the corrosion resistance, nickel is for the stabilizing the austenite phase, molybdenum is increasing the corrosion resistance, particularly against pitting and crevice corrosion, while carbon will affect the hardness and strength. And we need to take care about carbon. If you have a more carbon, then that's where it will leads to carbon precipitation, and when it also increases the hardness, decreases the ductility. So that's where the carbon percentage is more important. And as you know this, there are different types of stainless steel, like a ferritic stainless steel, austenitic stainless steel, martensitic stainless steel, dual phase stainless steel, and then final one is precipitation hardened stainless steel. That we have already discussed in some other videos, but we will cover it in upcoming videos as well. The next important question for interview is, what is powder metallurgy and where is it typically used? So as you know that powder metallurgy involves shaping metal powders into desired forms and then heating them to just below their melting point to bond them without melting. So So it is used in application where precision, uniformity, and the production of complex shapes are parts from difficult to I mean, if some important application in which you cannot do this machining process, then it is most important, like in automotive parts and aerospace components. But usually this powder metallurgy, as the definition has suggested, that it involves shaping metal powders into desired forms and then heating them into just below their melting point. So from lab purpose, what we have used here, I mean, I have also used the powder metallurgy route. So we usually first prepare the powder, that is using ball milling, and then we use SPS, which is plasma, a sintering plasma, this spark plasma sintering. So yeah, so this equipment is used to do this second step, that is heating them to just below their melting point to bond them without melting. And that's how you can use this powder metallurgy. But there are various application of powder metallurgy as well in automotive and aerospace components. So the next setup question is, describe the process of annealing and its purpose. So this is most important question if you are going for some job related to quality control, even if you are going for jobs for PhD or some master's level job. So they will ask about the heat treatment. So in heat treatment, this is most important question. Describe the process of annealing and its purpose. So basically, annealing involves heating a metal to above its recrystallization temperature, maintaining that temperature, and then cooling it slowly. This process relieves internal stresses and it increases the ductility. It refines the grain structure to improve machinability and the mechanical properties. So there are various type of annealing. It's just a basic definition of annealing I have shown here. But recently I have posted uh, one uh, one informative post on our LinkedIn page, where we have described the different types of annealing. Like you know, this annealing is having different types, right? Like for this, for example, we have a full annealing. We have the second type, like diffusion annealing, and then we have recrystallization annealing, we have process annealing. So these are the different types of annealing, and there is one another, stress relieving. So I have tried to define all the types of annealing there, but I will make a separate video on this as well. But the main purpose of doing annealing process is to relieve the internal stresses, to increase the ductility, refine the grain structure, and to improve the machinability. So these are the important things. Next question is, what are the key consideration in selecting materials for high temperature application? This is again very important if you are going in the industry which uses usually high temperature. They are working on high temperature applications, so they will ask you the what are the key consideration should be used for selecting the materials. So the first most important which we have like factors include thermal expansion, thermal conductivity, resistance to oxidation, creep resistance, which is most important. That's why if I'll give you an example of like I mean, you know, the turbine blades, right? These turbine blades are usually made up of this a single crystal, a nickel base alloy, right? So they have a high creep resistance, and some other like maintaining mechanical properties at elevated temperature. This is again like if you have, I mean, if you are working on some alloys like aluminum based alloys or something related to magnesium alloys. So what happened, they usually showed a very high mechanical properties at room temperature, but when you will heat this, I mean, when you will test these alloys at high temperature, like let's suppose greater than 200 degrees Celsius, so we are not able to retain the mechanical properties what they have found it out at room temperature. That's why they are going with some alloys like titanium based, nickel based alloys to use for the high temperature application. But nowadays they are also working on this aluminum alloy, something to find out, because the advantage with aluminum is that it is lightweight alloy, right? If it is lightweight and if you are able to maintain at higher temperature, then it is very good options to replace the titanium and nickel, because titanium and nickel is a highly dense material, right? So this is low density material which will be again very useful. So this is so a basic if they ask you, so you can answer like it should be highly, I mean it should be high creep resistance, resistance to oxidation, thermal conductivity, thermal expansion, and it will maintain the mechanical properties at elevated temperature. So examples you can say tungsten or alloys like inconel might be chosen for this one. Now let's go to the another set, which is how do you ensure quality control in metallurgical process? So this question will definitely ask you. I mean, if you are going for some industry job for the quality control job, so the answers would be like through non-destructive testing, NDT method like ultrasonic testing, radiography, magnetic particle inspection, and by implementing statistical process control to monitor production parameter. So this is just a basic answer I have given here, but I will try to make a detailed video on this particular question. The next one, what steps would you take to analyze a metal fatigue issue? So let's suppose they will ask some kind of practical or this problem solving question. So they will ask you, what steps would you take to analyze this metal fatigue issue? So for this for this question, you should first understand what is the, I mean, what is this metal fatigue, right? So this thing you should know about the fatigue. I mean, what is a fatigue, I mean how this fatigue failure will happen, how you can increase the fatigue life, what is the fatigue resistance. So the answer for this question will be like analyze the fracture surface for sign of fatigue. So first of all, you can examine the stress condition under which the part failed. Like if you are doing some fatigue testing, you know that you have to apply some stress condition, like some stress amplitude. You are doing this test as some stress amplitude, and this stress amplitude is below to the your yield strength of the material, and then at this stress amplitude to how, I mean to how much how many cycle that will go on, and then they will fail it. And then you can examine this fracture surface. You can see the beach marks, striations, you can see where the crack is nucleated, how it is propagated, and then you can say that about this about, I mean about the, if some issue is coming, you can say that okay, we can, I mean we need to reduce the this stress level. We can go to the this alloy production state and try to do some kind of alloying or something, right? And then review any previous similar failures. Conduct material testing for fatigue properties. So this is what I just explained. You can conduct the material testing for fatigue properties and consider redesigning for reduced stress concentration for using different materials. This is how you can analyze a metal fatigue issue. And also you can improve the fatigue property by introducing some kind of a compressive residual this compressive stresses into the material. So this is how you can address it. Now the next question is, last two question is like they will ask, how would you handle a situation where there is a discrepancy in material specification versus actual product performance? So let's suppose there will be discrepancy in the material specification what they have provided, and how the and when you are performed in the real application, it is not performing as it is mentioned there. So how you can handle it? So first you need to verify the testing method, retest sample if possible, check for any processing error, review the material supply chain for deviations, and consult with suppliers or metallurgists for a deeper investigation. So this is how you can solve this kind of problem if you are having it. The last one is, tell me about time when you had to innovate or improve a metallurgical process. So this is just a general question. So in this you can you can look for example where the candidate have shown initiative, used their metallurgical knowledge to solve or improve efficiency. So this is how you have to explain, like in your bachelor's, master's, or PhD. Have you ever innovate or improve something during your if you are doing some projects either in diploma level in BTech level or in master's level, how you able to innovate or improve the processes. Maybe have you, I mean you have developed a new alloy for that situation, you have developed a new testing method. Are you able to develop the alloys for new applications? I mean, you have used the already existing alloy for the alloy for the new application. So these are the things you can explain in this. In this particular question. So yeah, that's all for today's video. So I will come up with more questions in the next video. If you have any doubt or any questions, you can write down into the comment section, or you can contact us on LinkedIn or Instagram, Telegram, anywhere. So we are present everywhere. Yeah, so thank you so much.